Alright, in today's video I'm going to be talking about capacitors. Okay, and what I mean by capacitors, specifically non-polarized capacitors. Now, obviously everybody is familiar with electrolytic ones, and they are polarized. They got the positive and they got the definite negative sort of legs. If you swap them, obviously they would sort of go faulty and start smoking, and etc. etc. That will short out altogether. In some cases even explode, depends on the voltage and capacity of the capacitor. Nonetheless, this is a non-polar capacitors that we're going to be talking, and there is variety. You get them made out of polyester, out of polypropylene, mylar, polycarbonate, polystyrene, Teflon, and paper capacitors, just a few to mention. There is, of course, several more, but nonetheless, this is the most popular sort of capacitors. Now, this is a sign for capacitor, and it's a non-polarized. Okay. Now, why are we talking about the capacitors non-polarized today? Is because a lot of people, especially in today's electronic noise, is giving them a lot of hassles, hums, problems, glitches on their sort of electronic devices and things like that. And people wonder why. Is there actual polarity to a non-polarized tapotin? Well, the answer is no, and the answer is yes. When I say no, I mean yes, it's polarized. What I mean by that, if you look at it over here, okay, onto the structure, let me just sort of shift a little bit more. Okay, if you look at it, the structure of the capacitor, cross-section of the capacitor, you will see there is a first terminal. And the first terminal would be something like this. Okay, and then you get a second terminal, which would be another wire, or something like this. Okay, tapotin. Now, what they mean by first terminal, okay, when they manufacture and when they wind a capacitor, okay, there is a beginning and there is an end of the actual sort of capacitor, because basically it's either in a circular manner, sort of wound, sort of silver plates with some kind of an isolator in between tapotin. But there is a beginning and there is an end. Now, in the olden days, they used to mark and they used to put, and this is the actual end of the capacitor. In other words, it's an outer layer of the capacitor. And then on that, after the outer layer, there is a sort of isolator, and then there is an inner layer which is connected to the basically a first terminal. Now, why is it so important? Oh, well, it is quite important because, and I will demonstrate it now, for a very simple reason, because of the electronic noise, as I said. We live in the environment where you got routers, you got too many switch mode power supplies, welding machines, all sorts of TVs with switch mode power supplies, which all of them generate the noise. And the hassle is becoming more and more, sort of creating a basically RFI EMI pollution. That's a radio frequency interference pollution, which can severely interfere with some circuits. Now imagine, this is, as we said, if you look at it over here, this would be the, okay, let me do it this way. Yeah, this would be the first terminal, okay. So that is basically the beginning of the capacitor when they start winding it, okay. And then, you know, you can see this is different layers of the sort of starting foil of the actual capacitor. Then over that foil there is across each layer there is sort of some kind of isolation, and then you get a silver plate again wound. If you look at it over here, that's a plate, it's basically wound on top of it. And it ends up that the last layer on this particular this type of capacitors, non-polarized, is actually the outer layer. Now, being an outer layer, say for example, we got a hot, and this capacitor, say, has to be connected to pass the signal to ground or as a filter, or many different sort of applications for the non-polarized capacitors. Nonetheless, let's assume this is a hot and this is the negative, which in actual terms is not really negative, but it's an outer layer. Now, if it's connected, say, to ground, this outer layer, and the hot is over here, obviously that ground is actually shielding this capacitor, so the external interference or even internal interference from the electronic units will not be able to reach very easily the large area of the first terminal, if you look at it over there, the first terminal, okay, which is the starting point of the capacitor. So which means it's actually like a shield across the capacitor. If it's reversed, okay, and you start over here, okay, now that's an incoming, say, signal, and this is a sort of outcoming of the capacitor to ground. Now, obviously, only the center point, which has got what you call it, it's not shielded. It's not shielding the capacitor, so it's got a very large area for picking up interference, electronic RFI EMI interference and signals, unwanted signals, in other words. So, okay, without further ado, I'm going to demonstrate how do we know. As I said, in olden days, they used to mark with the black band the end of the capacitor. And that means the last layer is actually should be going to ground, let's put it that way. So it's like a shield of the actual capacitor. So you don't swap the capacitor. It won't harm it, but it can be, detrimental to the circuitry and performance of the complete unit because it will pick up any sort of electronic interference. Now, how do we test it? Very simple, okay? Everybody so far that I have seen, they have used scopes, state-of-art scopes, which are quite expensive. Of course, we do have a scopes. As a matter of fact, I've got a dual beam 100 megahertz on my bench, but nonetheless, it's not within the reach of many shop owners even. So how do you test it? How do you determine? Very simple. Most of the guys, they will remember it's called the signal tracer, signal injector. Now, what it is, it's basically an amplifier which has got sort of attenuation that you can have the full signal, very high gain amplification, or you can go in 20 dB sort of steps to attenuate the actual signal. Plus you got a variable. So basically what it is a very powerful, very sort of strong amplification. You feed a very small signal and you amplify it to quite a substantial sort of output, which is fed to the speaker and to the VU meter. In this case, I can route it via this switch here. Plus, it's got the injector generator, which we're not going to use right now. Also, the same instrument can be used for RF. Of course, for, lower, for very rough sort of determination of the RF presence and so on. But nonetheless, we're dealing with, signals. So I'm going to put on the AF sort of switch so you can actually visualize. So basically, I've got a cable, screen cable, connected into the instrument input of the input as you can see it over there, okay, into the two crocodile clamps over here. So let's assume, according to this diagram, okay, this second terminal, which is this one here, should be connected to the negative in order not to pick up a noise, okay, to shield the actual capacitor inside. So let's test it. Let's put it through a test. Okay, I'm just going to join it. I'm going to increase the gain over there. And now, watch now when I bring the finger. Okay, you can actually see, okay, you can see, okay, it goes up to about 3 or so. Okay, you can see it on the, and I don't know if you can hear the hum through the actual speaker. Now, let's see what happens if we connect it up wrong way. What will happen? Will it increase the noise or decrease it or whatever? Theoretically, it should increase the noise. Watch now when I bring the finger. Look at it. I'm not touching the wires, I'm just touching the capacitor. Look at it. Much more noise gets induced. And the reason being, because now this is the actual, if you look at it over here, look at it over there, now that's supposed to be a grounding point which shields the capacitor, but now it's connected to the hot wire. So this is why this capacitor is prone to a lot of noise, picking up any sort of interfering signals, and then it can introduce them into the circuits, which will now cause havoc, glitches, distortion, etc., etc., etc. In other words, it will be detrimental to the electronic units and circuitry that you're trying to build or repair. Now, let's try another capacitor, okay? Here is another one. Again, we got a black stripe, which indicates that would be our second terminal, if you look at it over there, okay, which is ground. Let's connect it up the right way and then see the difference. Okay, now watch when I bring the finger. Okay, very, very, very little. Let me just increase. Okay, okay, you can see I'm touching the capacitor. So it's very, very, very little. Now I'm gonna reverse the capacitor and let's see what happens now. Look at it. When I touch the capacitor, how much more if I do not connect the appropriate way capacitor into the circuit. So here is the proof, and very simple way of you determining. Let's go to another sort of shape of capacitor. Let's take this one here, and this one here is 1 microfarad. Okay, because it's not marked anywhere. Okay, I marked it over here because I did measure it in past. Okay, so I'm gonna connect it up. Say, let's see. Okay, watch now when I touch. Okay, you can see it's about 6, or number 6 over there. Okay, let's try to put it the other way. And the smaller deflection of the meter would indicate that is the right way. Okay, can you see? There is virtually zero. Virtually zero. Okay, it's the same cap except I reverse the legs. Okay, and it corresponds to my marking over here on the capacitor. You can actually see it. Okay, so that should go always to a low potential or ground of this non-polarized capacitor. And that way you will definitely eliminate the noise. Let's try another capacitor. Let's try, now this is one of the top-notch, capacitors, manufacturers, Vima. Let's try it. Let's see. I don't know. I haven't tried this one. Okay. Let's see what happens now. Okay. Can you see now? It's showing about between 10 and 6, plus minus, somewhere there. Let's reverse it. Okay. Okay. It just reaches just 10. So that would be the right way. As we said, the smaller deflection and smaller noise on through the speaker that we're getting, okay, that would be the right way. In other words, wherever this black is, that should go to a lower potential. The capacitor should go to a lower potential. So what I would do is, I would take a pen and I would put a dot to mark it, that would be my negative of the capacitor. And what I mean, not in a true sense, but that would be the actual shield over the capacitor. So yeah, on that note, basically, if you look at it over here, let me even demo you this particular one, okay, which I have got the picture here. And you can see on this particular capacitor, manufacturer has already determined where is the second terminal, which is the ground, and or lower potential, and where is the actual first terminal or the input. Let's put it across. Let's put it the right way and see what happens. Okay. Now, okay, let me just, get the reference. Okay, so from there, I touched that, okay. Can you see? It just goes over to number 1. It's on number 1 if you look at it, okay. Now let's reverse it. Now that ground will go to hot and see how much more noise do we get. Okay. Look at it. From 1 it has gone to something like 3. Plus 3. Which is substantial amount of noise that it's actually picking up. So this manufacturer has done a very great job and has pointed out to the consumer, whoever is going to use to the user, that would be your negative, or it should go to a lower potential or ground, and this would be your hot or the input signal property of the capacitor. So yeah, on that note, I will end up the demonstration, and I hope that you did understand what I was trying to actually convey, and the importance of which way you connect a non-polarized, whether you connect it up this way or you connect it up that way. Depends which way. That way, or you can swap it, and it makes a heck of a difference. Yeah.